Okay, well, welcome back to NCGNT in Prague. And today's talk will be by Andrea, our local speaker and one of the freshman members from the Charles University, Mathematical Institute. And the title of his talk will be on Ševera's quantization of Lie bialgebras. Please, the floor is yours.
Thank you very much for the introduction, and also thanks to Lucrezia for the pre-seminar. So yeah, the aim of this talk is to introduce this Ševera's quantization of Lie bialgebras. So we will gently introduce Lie bialgebras and then we will go to the result. Before that, just a brief introduction, or an historical introduction. So in general, quantization for us means to be a functor from assigning to any classical object a quantum object with some good properties. Today for us, classical objects are going to be Lie bialgebras, and on the other side, the quantum objects are Hopf algebras. So the first quantization of Lie bialgebras historically is the quantum group of SL2, and this appeared in 1982 in a work of Kulish and Reshetikin. Then in 1985, Drinfeld and Jimbo independently generalized the construction from SL2 to any symmetrizable Kac-Moody algebras, and today we call this class of objects the Drinfeld-Jimbo quantum groups. Then in 1989, Drinfeld defined this object, which is called Drinfeld associator, and we are going to see that this is a very crucial object for constructing a universal quantization functor. And 3 years later, he asked some problems in quantum groups theory, and among these problems, there was the problem of the question of if it was possible to quantize any Lie bialgebra in a universal way. And the positive answers came in 1996 by Ettingov and Kashdan, and 20 years later, Pavel Ševera gives a new construction. So this is the outline of this talk. In the first part, we will see our classical objects, which are Lie bialgebras and their representation theory. I'm not going to talk about the quantum objects, which are Hopf algebra, since Lucrezia did an amazing job in the pre-seminar. Then in the second part, we are going to introduce topologically free modules, and we are going to define what is a quantization of a Lie bialgebra. In the third part, we will see how to deform an infinitesimal liberated monadal category using a Drinfeld associator. And finally, we will show the Ševera's quantization, we will exhibit, and if we have time, we also will see some properties of the Ševera's construction. So let's go with the first part. So as usual, Lie bialgebra is a pair where we have a vector space G and a Lie bracket, which is a linear map from G tensor G into G, satisfying two properties. First is that the Lie bracket is antisymmetric, and the second is the Jacobi identity. What you can do, need some red? Okay. What you can do here is the following. So you can represent the Lie bracket with the following picture. So we read this picture from left to right, and this is the Lie cobracket, the Lie bracket. And in particular, from left to right, so it has two inputs and one output. If you do so, you can represent the antisymmetry of the cobracket with this picture and the Jacobi rule with this one. This pictorial representation can be useful later on in order to understand some axioms. For instance, in general, in category theory, you can do the following. You can take a definition, you can reverse all the arrows, and in this way you obtain the dual definition. And this is exactly the way how to define Lie coalgebras. Indeed, a Lie coalgebra is a pair, again, where we have a vector space C, a map, linear map delta, and this time the map goes from C into C tensor C. And now we require that the dual axioms of a Lie bialgebra are satisfied. So we have the antisymmetry of the Lie cobracket and the co-Jacobi identity. So this is the algebraic formula for the axioms, and this is the pictorial one, in which you see we reverse all the directions with respect to the Lie algebra axioms. Just another thing, here we can also use Wheeler notation for the Lie bracket, as in the case of algebras. And another thing I have to say is that I will denote by tau the usual flip in the category of vector space. Okay, and then Lie algebra is exactly what you expect. So we have a vector space together with a structure of Lie algebra, a structure of Lie algebra, and these two structures satisfy a compatibility condition, and this is called the cocycle condition. It is given by this formula. So you can write in a Schwider notation or in one more compact form. And also you can represent this in pictures, which the left-hand side here. So you note first we apply the Lie bracket and then the Lie bracket. And on the right-hand side we have the four terms. Okay. Just a very small example, which is very nice. So take the usual vector space SL2 with the standard generators E, F, and H. You know that this is a Lie algebra with the usual Lie bracket. And what you can show is that this is also a Lie bialgebra, and the Lie co-bracket is given on the generators by this formula. So the Lie co-bracket of E is equal to 1/2 E tensor H minus H tensor E. Same formula for F, and the delta is 0 on the Cartan subspace. This is, for us, this is called the standard Lie bialgebra structure. This is not the only Lie bialgebra structure you can put on SL2, but we refer to this as the standard one. Okay. If I remember correctly, there are three different ones in which you have a little R matrix. But to be honest, I'm not 100% sure. So of course you have the zero bracket. This is a Lie algebra structure. Then you have this one, and yeah, I remember there is another one. I don't know if there are more than three.
Basically asking to find E brackets on the dual space, right?
Yes. Yes. Mm-hmm. Thanks for your question. Okay, so we can go on, and okay, so recall the quantum objects are Hopf algebras, and Hopf algebras have Dirichlet modules. We say that the classical objects are Lie bialgebra, so we have to define something similar. And for us, this representation theory on this kind is called Dirichlet modules. So we swap the order of the names just to distinguish the two concepts. And this is the following. So take B a Lie bialgebra and V a vector space. So we said that V is a Dirichlet module over B if there are two maps, two linear maps, so pi and pi star, in which pi star is not the transpose of pi. This is just a notation. And more specifically, pi is a linear map from B tensor V into V, and pi star is a map from V into B tensor V, such that these two maps satisfy three conditions, in which the first one is telling you that pi is a left Lie action on the Lie algebra B. The second is the fact that pi star is a right Lie coaction on B. And then we have, again, a compatibility condition between left action and right coaction. And in this case, you can also represent with picture all these axioms. In particular, we choose a color for the vector space V. This today is green. And you can represent the action in the following way. So the black string, wait, every time this, sorry. The black string represents the vector space B, And the green one represents the vector space V. So this is our action. And then the dual picture is the coaction. And for example, now it's pretty nice to see that this long formula is represented by this equality of pictures. And these are our Dreamfield-Jeter modules. And as usual, you can define a morphism of Dreamfield-Jeter modules, and these are just morphisms of Lie modules and left Lie modules and right Lie comodules. And you can form the category of Dreamfield-Jeter module, which we denote by dy. And you can show that this is exactly a symmetric braided monoidal category in which the constraints are the same of the category of vector space. And in particular, if V and W are two Dreamfield-Jeter modules, then also the tensor product is 2, and the structure is given by the following formulas. In this case, the pictorial representation is the following. So we choose the green color for V, the blue color for W, and then we have that the action is represented by this diagram, and the coaction is represented by this one. And this is symmetric braided model category. Later on, we will show that this is also an infinitesimally braided model category, and this is going to play an important role for our purposes. And okay, for us, it will be very important the following Dreamfield-Jeter module structure on the universal enveloping algebra. So, as usual, take B bialgebra, and you can form its universal enveloping algebra, UB. And you can show that there exists a unique Dreamfield-Jeter B-module structure on the universal enveloping algebra satisfying these three conditions. So the first is that the Lie action is the joint action. The second is that the Lie coaction is 0 when evaluated in 1, and it is equal to minus delta of x when evaluated on the elements of the Lie bialgebra. So this is a Dreamfield-Jeter module, and also we have some extra information. So you know that this is an Hopf algebra, so we have co-multiplication. You know that this is a co-commutative one, but in particular, this is also co-commutative in the category of Dreamfield-Jeter modules, meaning that this is a morphism. Yeah, sorry. It's a bad mistake. Yeah, ux, of course. Okay, so yeah, we will need this Dreamfield-Jeter module structure and the universal enveloping algebra. And again, we will show that this, I mean, we will not show, we will just mention that this is co-commutative, but also infinitesimally co-commutative. We will see what this means. Okay, I think, yeah, this concludes the first part. Are there any questions so far? Okay, very good. Okay, now it's time to define what is a quantization of a Lie bialgebra, and since quantizing means deforming, we need the formal parameter. And then we need to talk about the ring of formal power series with coefficients in K. So take field K, just I will write somewhere, probably here. What is happening? Okay. The characteristics of the field is 0 for today. And okay, so take formal parameter H bar and consider the ring of formal power series with coefficient in K. And then for any vector space V, you can form a module over the ring of formal power series just by considering the formal power series is with coefficients in V. So this set. And this is a module for the ring of formal power series, and the action is exactly what you expect. So it's the usual formula. And in particular, in general, in the theory of the modules of the ring of formal power series, we say that a module is a topologically free module if it is isomorphic to this kind of module for some vector space V. And we shall use this category later on and shall denote by this nice T. Okay. And okay, you can show in particular that this is a symmetric braided monoidal category in which, in order to obtain the constraints, you just take the constraints of the vector spaces and linear extend everything. So basically, and for the tensor product, you take the H bar adic completion. And then you have a braided monoidal category. And as Lucrezia mentioned in the pre-seminar, you can consider a lot of things in this category. For instance, you can consider Hopf monoids. And we define a topological Hopf algebra exactly in this way. So we take an Hopf monoid in the category of topologically free modules. And more concretely, this consists on this data. So we have H, which is topologically free modules, and then we have 5 maps. We have the multiplication, unit, co-multiplication, co-unit, and antipod. And now these are formal power series of maps. And we require that the usual axiom of Hopf algebra is satisfied, are satisfied. And this is a topological Hopf algebra. So now, finally, we have the ingredients for this definition. So let B be a Lie algebra and H be a topologically Hopf algebra. Then we say that H is a quantization of B if there exists an isomorphism of Hopf algebras of this form, such that you can reconstruct the Lie co-bracket of B through the co-multiplication of H with this formula. So you take delta, so the Lie bracket of X is equal to the multiplication of X tilde, where X tilde is any lift of X in H through this isomorphism, minus delta op over H bar modulo H bar. And this is the definition of quantization of a Lie algebra. And as I mentioned before, Drinfeld in 1992 asked if it was possible to quantize, to define a quantization functor, actually a universal quantization functor. Today we will not have the time to talk about universal quantization functor, but you have to think to all these functors in a universal way, meaning which means using props in some sense, for any arbitrary Lie algebra. And we know that the answer is yes. We will see how to do it. And this is, as I mentioned before, the first example of a quantization of a Lie algebra, and it is the quantum group of SL2. So in order to define it, take the free algebra generated by free elements, which we call big E, big F, and big H, and put these relations of the algebra. So note that for these two relations, these are just the usual relation of the universal enveloping algebra, and the third one, so the bracket of E and F, is now a deformed relation and is equal to this quotient of exponentials. And you can also see that this is equal to H plus something else with H bars. This is actually an Hopf algebra with the following co-multiplication and antipod. And you can easily see that this is a quantization for the standard structure of SL2, which we defined before. And in particular, you see that modulo H bar, this is just the universal enveloping algebra relations. Also, the co-multiplication become the usual, and the antipod become the usual one of the universal enveloping algebra. You should also compute this term. You can do as an exercise. This is easily okay. Okay, so this is the example of quantum SL2. Yeah, exactly. I think, to be honest, probably You have to put 1/2 here if you want in any exponential. If you want exactly the same on the exactly that generators. But yes, it's that one. Okay. Okay, very good. So we finished the second part. Are there any questions or comments? If not, we can go on with the third part. So deforming infinitesimally braided monadal categories. So again, I want to thank Lucrezia because she introduced a lot of topics for this seminar. And in particular, we will need a lot the concept of infinitesimally braided monadal category. If you follow the seminar, the pre-seminar, for us, these are symmetric Cartier. So this for us is an infinitesimally braided monoidal category, and it consists of a pre-additive braided monoidal category with an additional natural morphism T, and then we have again associativity constraint, left and right unit constraint braiding, which are all of them are natural isomorphism, and we have this additional one, the infinitesimal braiding, which is not necessarily invertible. And then, of course, we ask, as usual, that we have the pentagon axiom, the triangle axiom, and the hexagon axioms for the first four isomorphisms. And in addition, we ask that the infinitesimal braiding satisfy the following two relations. The first is the commutativity with respect with the braiding, and the second is this linearized braid condition. And also, for me, a category is said to be strict if the associativity constraint, the left and right unit constraints, are identities of the category. Symmetric braidings. Yeah, you're right. You're right. I mean, in general, no, but for this talk, yes. Because, yeah, we will take just the flip, I would say. Infinitesimal braiding? Yes, you can do it. We talked with Thomas. There are several ways to do it. Some people represents, okay, so now it's better to do from up to down because from left to right is not the best for this kind of pictorial representation. So some people can do like this for the braiding, for the infinitesimal braiding from up to down. I mean, I like this one, but I like that up to homotopy, everything is well distinguishable. So this can be thought about the identity up to homotopy. So I personally prefer something like that. So you just put a box when you have a morphism. This is our T. You can, yeah, you have this in general. Yeah.
Some topological.
You have topological interpretation for the axioms of, for instance, for the braiding. I don't. Yeah, is the usual. Yeah, is the usual braid relation. Yes. So excuse me, which Jacobi identity in particular, the one of before, or?
Yeah. So yeah, Jacobi identity.
For Lie algebras.
Yes. Yeah.
Okay, so for that kind of categorical, for pictorial representation, we use again from left to right, and Jacobi identity is the following. So you take the Lyco bracket and then another Lyco bracket. And this, okay, you put here. I don't have so much space. So you compose this with the identity plus this with this permutation and then plus the other one. So like this. And this is 0.
So my question is basically how to properly apply this infinitesimal braiding to this equation. So whenever I have V times a V, I would like to apply this T.
Uh-huh.
So how is it going to be reflected on the diagram? So whenever we have an intersection.
I see your question. Yeah, that's true, but we will see later on that no, okay. The real question is, but do you have an infinitesimal braiding for Lie algebras? Lie algebras.
Yes,
I don't know if you have some, yeah?
Maybe there is a paper of Heckenberger and Bentham, and there they define a notion of a infinitesimally braided Lie algebra. So there's like an extra term that has the T. Maybe for this talk, but much.
Okay, so it's another generalization. Okay. Yeah, I don't know. Yeah, exactly. Classically, T equals 0 is, so you don't have it. Thank you very much for the question. Okay, so these are our infinitesimally braided monadal categories. And the main example for us today are the following two. The first is the category of vector space V. This is infinitesimally braided with trivial infinitesimal braiding. As Lucrezia said, every braided monadal category is infinitesimally braided with 0 infinitesimal braiding. And the second example is the most important one for us, saying that the category dy of Drinfeld-Dieter modulus of a Lie bialgebra B is infinitesimally braided with this infinitesimal braiding. So here in pictures, now we come back to the left to right notation. This is our pictorial representation for TVW. And basically, you just, again, here we denote the vector space V with the green color and the vector space W with the blue color. And basically, you start here, you coact with respect to V, and you act on W plus the other direction. So you coact and then act. And this is our non-trivial infinitesimal braiding for this category. And as you can expect, again, since there are infinitesimally braided monadal categories, there are infinitesimally braided monadal functors. But yes, this is the flip. Yeah. Thanks for the question. Yeah, it's not really clear. This picture, you should think to the braiding as this part, no? There is a crossing, so this is the when the braiding acts.
That's a bit strange, right? Because usually the data modules they are braided with an honest braiding. But here we are in my algebra case, so there is a bit.
Yeah. It's a bit. Okay. Yeah, exactly. Okay, so I was saying that you have also infinitesimally braided monadal functors, but we are particularly interested in comonoidal functors. So take the definition of monadal functor and basically reverse all the arrows. This is the following definition. So comonoidal functor from B to C is given by a triple, G, G2, G0, where G is a functor, G2 is a natural morphism indexed by all the pairs of objects in B, and G0 is just a morphism from G of the identity of the tensor identity of B to the tensor identity of C. And you ask, of course, that some diagrams are satisfied, are commutative. In this case, just for space reasons, also because Lucrezia introduced the same diagrams before, I just put the strictified versions. And in particular, if G commutes also with the bradings, we say that it is braided comonoidal. And if it commutes with the bradings and also with the infinitesimal bradings, we say that it's infinitesimally braided comonoidal. And also, this last definition will play a role. So if both G2 and J0 are invertible, we say that G is strongly comonoidal. Okay. So I said before that we want to deform infinitesimally braided monoidal category from using a Drinfeld associator. Then I have to define it. This is just a formal power series which we denote by phi AB with coefficients in K and in two non-commutative variables, A and B, satisfying the following five conditions. First is group-like with respect to the primitive coproduct on A and B. Then it is invertible, and the inverse of phi evaluated on A and B is equal to phi evaluated on B and A. And finally, the two very important properties, so the pentagon and the hexagon equation. First, the pentagon equation is the following. It's very particular and holds for any elements A, ij satisfying the infinitesimal braid relations, which are these three families of relations. And finally, the hexagon equation, which is the last one, and this holds for any elements A, B, and C, such that the sum, which we denote by lambda, commutes with all of the three. So lambda commutes with A, with B, and with C. And this is a Drinfeld associator. I just mentioned that Drinfeld showed that in characteristic 0, there always exists an associator, so we are just fine. And the way to deform the infinitesimally braided model categories is explained in this slide and appeared in probably in the first time in the paper of Cartier in 1993 and states the following. So take C be a symmetric infinitesimally braided monoidal category. You take a Drinfeld associator and a formal parameter, and then you can construct a new braided monoidal category, which we denote by C phi. And here you keep the same object of C, and you take as a family, as class of morphism, you take the H bar adic completion of morphism in C. Same you do with the tensor product and the unit constraints, you just take the H bar adic completion of the old one. But now the very interesting thing is what happens to the braiding and to the associativity constraint. So start with the associativity constraint. The new one is given by the composition with the completion of the old one together with this morphism, which is the action of the Drinfeld associator, first in which our A is TUV tensor identity W, and then in the second spot, so our B is given by the identity of U tensor TVW opportunely composed with associators. So this is our a new Drinfeld, a new associativity constraint, which in general is super non-trivial. And the same for the braiding. So you take the composition of the old one, but completed with this exponential in which the infinitesimal braiding is acting. So the thing you need to see here is that in general, if your infinitesimal braiding is non-trivial, this is a non-trivial structure of braided monoidal category. In the case, if it is trivial, for example, here, if you take the category of vector space, and we know that this is infinitesimally braided with zero infinitesimal braiding, if you do this machinery, you obtain the category of topologically free modules, no? Because you have the same objects, the completed morphism. Well, it's not equal but isomorphic because there is this detail on the objects. But here, for instance, this term vanishes since t is 0, this term vanishes since t is 0, and then you obtain exactly the completion of everything, which is the category of topologically free modules. And similarly, you can do the same with functors. You can deform braided comoidal functor in the way that you expect, so in the same way, basically. Okay, then any questions? This one? Yeah. Yeah, basically you do exactly the same thing to the two categories, B and C, and you know how to deform morphism, and you do the same with the G0, G2, and G. G is basically the same on the objects and is completed on morphism, exactly the same machinery. Okay, very good. Okay, we are in the fourth part. Okay, we can see this Ševera's quantization, and this is basically you can divide the reasoning of this construction in 4 parts. So the first 2 are about category theory. Then we have some algebra, and then we have some deformed algebra, let's say. Okay, so let's see first the category theory part. Sorry for this. Okay, so first, given a comonoidal functor G, recall we have also G0 and G2, from B to C, and you take a comonoid M, which is again an object in the category in B, satisfying the usual axiom of coalgebra, but in the category B. So you take these data and you say you say that the functor is M adapted if some invertibility conditions hold, and this invertibility condition depends on G to G0, delta, and epsilon. So this is just, we will see more precisely what is the definition, but this is just to have an idea. And then you show that any M-adapted functor, G, give rise to an opmonoid structure on this object. Okay. Then you pass to the algebra part, and here we need to talk about Lie-bialgebras, vector spaces. So you build this functor C from the category of Drinfeld-Dieter modules to the category of vector spaces, and you show that this is UB adapted, so where UB is the universal enveloping algebra. And this, by the second part of the category theory part, will give you an algebra structure on the vector space C of UB tensor UB. And this is also isomorphic to UB. We will see everything I'm saying. But now you need a topological algebra. So you take a Drinfeld associator, you do exactly the same you did here, but in the deformed setting, and you build a non-trivial topological algebra structure on the universal enveloping algebra. And this is your quantization for your Lie-bialgebra. This is just the plan of the Ševera's construction. So we can start with the category theory part. And so take 2 braided monoidal categories, C and B, and a comonoid in B. You say that you take also a braided comonoidal functor C, and you say that it is M-adapted if for any pair X and Y in B, the following 2 morphisms are invertible. The first, we call it Km, and it's the composition of G of the counit with G0. And the second is gamma X, Y, M, and this is the composition with G of the identity tensor delta tensor identity with G2 G2 of X tensor M and M tensor Y. And of course, here in the middle, I need some map, just a composition of associativity constraints, because we need to compose the right brackets. So we need to go from this bracket to this one if we want to compose the right arrow and the left one. Okay, so this is the notion of M-adapted functor. And Pavel Ševera showed that there is another way for understanding these M-adapted functors, and this is the following. So you show that the braided model functor is M-adapted if and only if the following composition of functors, which we denote by GM, is strongly comonoidal. So you first tensor to the left with the comonoid M, and then you apply G. This is a composition of comonoidal functors, since you can easily show that the coalgebra structure of M gives you that this is comonoidal. And if the composition is strongly comonoidal, then you have that G is M adapted. Okay. And this is the theorem in order to build up algebras, and it says that if M is a co-commutative comonoid and G is M adapted, then the object G of M tensor M is an Hopf monoid. And the following, the structure is the following. So you just note that in order to have the monoid structure, or the algebra if you prefer, you really need that the functor is M-adapted, since you need to invert these two maps, Chi-M and gamma. On the other hand, the coalgebra structure is completely free, because you have that M is a comonoid, then M tensor M is a comonoid, and G is comonoidal, so sends comonoids to comonoids, and then the coalgebra, or if you prefer, comonoid structure is completely free, given by G. And finally, you note that the antipod is just the image of the braiding. So we denote in general a braiding by C, but if this is the tensor flip, it will be tau, just to clarify this.
So this EM adapted, is this basically what you need in order to get a new associative? Or there was some condition on
It's okay. You need, of course, that is adapted in order to have associative multiplication. But if you see just the definition of the multiplication, you just, in order to define the multiplication, you need that is M adapted. So if it's not, you don't have a multiplication which is not associative. You just don't have a multiplication.
gamma is invertible.
Uh-huh.
Then
In order to show that this is associative, you don't need. If you know that gamma is invertible, this is associative. So, okay, probably your question is if gamma is invertible but the functor is not adapted, this is still associative. The answer is yes, but still you don't have a unit. So, yeah. Yes?
So then probably a good notion of homomorphism of M-adapted comonoidal functors, right? So it's like a natural transformation plus some compatibility with
That's a very interesting question. I don't know.
I was just wondering if there is something like the most universal M-adapted.
Uh-huh. Yeah, probably one can do it because everything seems to behave very well. That's very interesting. Thanks. I will try to see this next days. Thanks. Are there any other comments or questions? Okay. Okay, so let's go into the algebra. So take a Lie algebra B and set M be the universal enveloping algebra. So with this data, you can consider the following comonoidal functors. The first is the functor of coinvariance from the category between Foglietto models to vector spaces. Then, sorry, I said coinvariance, I mean the forgetful functor. So F, coinvariance C, from again the category of Drinfeld-Dieter models into V, and assigning to this, to a Drinfeld-Dieter model V, this quotient. And then you can do the same of C, but composed with the left tensor multiplication, tensor product with M. So we have three functors from the category of Drinfeld-Dieter models into the category of vector spaces. And you can show in a very explicit way that the functors F and Cm are naturally comonoidal isomorphic, and in particular, these formulas gives you the natural isomorphism. So very well, you have some connection between F and Cm, very explicit one. And note that this implies that Cm is strongly comonoidal, since F is strongly comonoidal. The comonoidal structure of F is the identity one, so everything is invertible. And so Cm is isomorphic to something which is strongly comonoidal, so also Cm is strongly comonoidal. But we know that Cm is strongly comonoidal if and only if C is M-adapted. This is exactly this theorem. Okay. Then we have that C, the functor of covariance is M-adapted. And as you can imagine, this implies immediately that the object, or now we have a vector space C of M tensor M, recall that M is the universal enveloping algebra now. This is an Hopf algebra, and the Hopf structure is given by the formula before, as before, in which probably I forgot some theta M here and some zeta M. Okay, but unfortunately, if you compute by hand, you just see what we are talking about. Sorry again. You just obtain that this is the usual Hopf algebra structure of the universal enveloping algebra. So this is not really interesting in the non-deformed case. Okay. So in order to obtain something interesting, you need just to deform the categories with Drinfeld associator, but before you need to prove that M-dot functors preserve some good properties when you deform the functors. This is explained in this slide. So if B and C are two infinitesimally braided model categories, and you have infinitesimally braided comoidal functor, which is M, okay, no, not yet. So if you have M be a comonoid and phi be a Drinfeld associator, then if G is M-adapted, then also the G phi, which is the deformation of the functor, is M-adapted. And also if M is infinitesimally cocommutative, meaning that M is both cocommutative and this is the condition, extra condition you ask when you say that it is infinitesimally cocommutative, then the object M is cocommutative but in the category B phi, so in the deformed one.
Is there a TM missing?
Sorry, again, the TM?
Is it T delta equals delta, or should it be T delta equals delta?
No, it's just TM. There is no delta T, because delta is one input and two outputs. So you can do the other way. It's the same definition of being a cocommutative, but with the infinitesimal braiding. You see that since the cobracket, the comultiplication is of this form, you can't have a T before of delta. Okay. Okay. And okay, so being M-adapted is preserved by deformations in the sense of the one we told before. And also you can show explicitly that the universal enveloping algebra, together with the Drinfeld-Dieter structure as before, is infinitesimally commutative in the category of Drinfeld-Dieter modules. Then a consequence is that the same object, but regarded in the deformed way, is cocommutative. And then we are almost done. You can finally exhibit your quantization alla Ševera. And this is the following. So suppose take B be any Lie algebra and phi be a Drinfeld associator. Then you have a topological Hopf algebra on the universal enveloping algebra, and we denote this by U check B. This is a quantization of B, and the topological Hopf algebra structure is the following, in which you do exactly the same machinery as before. So you take the m dot functor, you construct the Hopf algebra, but now we have the deformed situation. So, for example, if you remember, gamma contained some associators, no? In the definition. Then now in the deformed picture, gamma is highly non-trivial because you recall that the associator, the associativity constraint here is given by the action of the Drinfeld associator on some infinitesimal braiding. So this is non-trivial. And also for the comultiplication, we have a very non-trivial map, since here we have the comultiplication of m tensor m. And if you remember how it works, so the comultiplication of a tensor product contains a braiding in the middle. And here the braiding is an exponential, so it's highly non-trivial. And furthermore, you can show that the functor assigning to any b this topological Hopf algebra is functorial. So we have a universal quantization functor. Okay, so this should conclude the fourth part. Are there questions? This is the main theorem of the talk. I know it's probably quite technical, but if you see very slowly, you will see that it's very a smart idea. I like it very, very much. Okay, if there are no comments or questions, I can very briefly show a couple of very nice properties of the construction. The first is the compatibility with Drinfeld-Dieter modules, or I should say Dieter-Drinfeld modules. I just resume this one slide. Okay, so we have, you can show the following lemma in the Ševera context. So consider again two braided monoidal categories and M be a commutative object. Again, you take an M dot functor, and you can show that for any object x of B, we have that the object G of x of M tensor x is a left-right Dieter-Drinfeld modules over G of M tensor M, and the construction of this structure is the following. And it's very, very interesting that here we have appear the inverse of the braiding. So this plays an important role. You really need to consider the inverse of the braiding in general. Okay, and then the result. So if you want some details, just I comment that the very pain of this result is the compatibility condition of these two guys. It's very long to prove. It's not easy at all. And then if you go into the concrete setting, take B be a Lie algebra and M be the universal enveloping algebra and the Drinfeld-Dieter module over B, which is our vector space V. And then you do the same thing, but with V, but in the deformed setting, of course. And you can show that the Dieter-Drinfeld module obtained this way. So basically, it's this one with x equal V, and in the deformed setting, this is a quantization of V, meaning that modulo H bar, the action is pi and the coaction is pi star. So Ševera is good also for quantizing modules. And also, the very nice property of Ševera is the compatibility with twist, which before was proved in a very complicated way for dating of Kazhdan quantization. So this is very short and work as follows. So recall what is Lie bialgebra twist. This is just an element satisfying this twist equation. And why do we care about twist? Because if you have a Lie bialgebra, you can twist it and form a new Lie bialgebra of this form. And similarly, if you have a Drinfeld-Dieter module over B, you can twist it and form a Drinfeld-Dieter module over the twisted Lie bialgebra. And this is the twisted Drinfeld-Dieter modules. You can show that the functor, this functor, so from the category of Drinfeld-Dieter modules over B to the category of Drinfeld-Dieter modules over the twisted B is invertible and infinitesimally braided monoidal. And also the inverse is T minus J. So if we call Tj this functor, the inverse is T minus J. And this allows us to consider the following objects in the category of Drinfeld-Dieter modus over B. So we have M, the usual Drinfeld-Dieter structure on the universal enveloping algebra, but now we have also N, which is again the universal enveloping algebra as a vector space and also as Hopf algebra, but the Drinfeld-Dieter structure now is given by this one. So it's literally another one. And you can show very easily that the functor of coinvariance is both M and M adapted. This happens because M and N have the same Hopf algebra structure, so it's a free result. But this implies in particular that we have two Hopf algebra, C of M tensor M and C of N tensor N. So very shortly, without giving too many details because I don't have time, you then show that C, the object C of M tensor N is a C M tensor N, C N tensor N bimodule via some maps. And next you pass to the deformed setting. So take this element inside this object, and you can see that this is not group-like, because if you see the product, you have this term in red, which again contains a braiding. So here, beta 2, 3, I didn't say what is it. It's just the middle for interchange when you have braiding. And this again involves exponentials. So this is highly not group-like. And you define a twist, J. So this lack of being group-like allows you to define a twist very briefly. And this is the formula for this twist. And you show very shortly that, okay, hi, Antonio. You can show that this is exactly a quantum twist and this a quantization of the little twist. So again, it's very fast, I know, it's very hard to see this in a couple of minutes, but just keep in mind the result. Some element satisfying this too, yeah. Yeah, I understand your question, yeah. So, okay, then this is the last thing I wanted to say, and I have some very short bibliography. I thank you very much, everyone, for your attention.
Thank you very much.
Very nice talk. So do we have questions in the audience?
If I understood correctly, you're saying that this quantization process of Ševera, it preserves the Drinfeld modules. But what about ordinary modules? I mean, so for the usual Drinfeld Jimbo, UQ of G, as I know them, the finite dimensional modules are the same in the classical and the quantum setting.
Mm-hmm.
So for general modules, what happens?
Well, you should. I mean, the Dreamfield Dieter models are more, no? So you can. But yeah, I mean, it's a model with another action, echo action, and we have more, no? So yeah, I have to see.
And then what happens on the Joule side when you're quantizing the coordinate algebra?
This is very good question.
Or can one just take these guys and then define the half Joule in some sense, like you do for Yetter Drinfeld, or for Drinfeld Jimbo?
But again, Dreamfield Jimbo in the finite dimensional case, you say.
Mhm.
Okay, this is isomorphic to the Dreamfield Jimbo case. This is just a concatenation of results. So I think of Kashdan in the sixth paper, they show that their construction is isomorphic to the Dreamfield Jimbo if you have symmetries epoch Katsumudi algebra, and Appel and Toledano Redo showed in another paper that the Ševera's quantization has some dual isomorphic relation with the Etting of Kashdan one. So,
but I guess like for more general situations, do you have a kind of a Joule analog of this quantization? Does it Jouleize?
in the
You see what
finite
I mean, I guess,
dimensional,
no?
in the finite dimensional.
Yeah, say.
Okay, this is actually a work in progress, and we would like to see if the Cassel to have P quantization works. So basically, you have in that scenario, you have a finite dimensional bialgebra, and they show that there is a two-parameter family of quantization, one quantizing one parameter for the multiplication, one for the multiplication, and if you pass the dual, you're changing the parameters, these kind of things. We are trying to do this right now with Martin Bordeman, and so I will tell you, I hope, soon.
Thanks. Could you please go to the slide where you had UB and defined the CM functor?
The CM functor.
Yeah.
Yep. Mm-hmm.
Yeah, I think it was
This one or this one?
If you go down.
CM, right.
Yes, here.
This one.
So what it does is, so you take the Jetta Drinfeld or Drinfeld Jetta module, and then you map it to this quotient. And I have to say, to me, this looks a little bit like the fundamental theorem of Hopf modules, because what you do you tensor with M. M is just UB. Yeah, so you tensor with a Hopf algebra, and then you quotient out the invariant elements. Yeah, so that's kind of the functor that tells you that the Jetta Drinfeld modules they are the same as tetra modules.
Okay.
And
okay, I see.
it's a bit funny that this. So I mean, it's not exactly the same, because here I'm talking about the quantum versions, not these algebra versions. But it's kind of funny. So this really looks like the fundamental theorem. And then it seems that what you're doing then, using this Drinfeld associator, you like build a twisted version of this fundamental theorem to get a deformed Hopf algebra structure. Is that right? So can I somehow understand this as some deformation of the fundamental theorem?
I don't know, to be honest, because I never thought this way to all of this.
Because the point is, so you said that if you don't deform this, then you just get an isomorphism of Hopf algebras and nothing changes. Yeah, and the fact that this is an isomorphism is the fundamental theorem.
These two, you mean these two?
Yeah.
Yeah, I mean okay. not really.
Okay.
So you have an isomorphism between these two functors, but now, since we want Hopf algebras, you use this isomorphism to always go into f of v. I don't know if. So, okay, you have a result on C of M tensor M. So C of M tensor M is an Hopf algebra. Good. But C of M tensor M is an Hopf algebra, and this is exactly Cm of M, right? By definition. And this is isomorphic to f of M, which is M, no? So we use the result on C of M tensor M to build the Hopf algebra, but in more practical way, you look here, inside M. And then this is why this theta and zeta appear in the theorem, no? But if you look, okay, so if you look like this, yeah, you're not deforming the universal developing algebra. But I'm sort of cheating because I'm using theta and zeta, no? So you should look at the result inside of C of M tensor M.
Okay, because you're saying later on you don't use zeta and theta, so
yeah, because you shouldn't use this. I mean, this is the Hopf algebra structure of M. This is not the one of C of M tensor M. If you want the one of C of M tensor M, you remove this, and you're done. But this is not. I mean, it's isomorphic, but it's not the same thing, you know.
Okay.
But yeah, for the other comment, but the interpretation of a twisted
Fundamental
version.
theory.
Yeah, I don't know, to be honest. Thanks.
More questions? All right, maybe some online audience. Please raise your hands, unmute yourself.
Okay, probably some.
I can't do the chat, but it's Antonio and Rita saying thanks for the talk.
Okay.
Thanks. Thank you very much.
So then we can move the discussion to usual watching. Thank you very much, and see you next week.
Thanks. Also, we have okay, shared.
So next week we have Dimitris Gerontogiannis coming to us from IMPAN in Warsaw, and he will speak about the log Laplacian on Alfor's regular spaces and non-commutative boundaries. And there'll be the pre-seminar with our own Freddie Diaz, who's back virtually in Prague. So yeah, hopefully we'll see you there.
Thank you very much.